Today on the Vulcan Way, 2.6a, graphing rational functions. So we're going to go ahead and get started right away because when you look at the note sheet, you can see the whole first column is just steps for these. And again, this is just steps to help you have a process for graphing these. So the first few examples are just practicing what's in each step of the steps to graphing rational functions, and on the back we'll graph 4 of them just so you get good practice. Okay, so let's start by defining a rational function. Hope you already know this because we've talked about it, but rational root word ratio, meaning that it can be written as a fraction. So that's what we're looking at. The domain is all real numbers except numbers that make the denominator equal to 0. Not something new for us. We knew that. So here's all the steps. Step 1 is to factor. So you always want to factor the function first so that if there's factors that cancel out, they get canceled. Step 2, holes. So sometimes there's holes in these graphs, and the way these holes are created are when the factor in a numerator cancels with a factor in the denominator, and it will occur at the x value that corresponds to the canceling factor. If you want to find the exact location of the hole, meaning you need x and y, you just take your x value from the hole, from the canceling factor, and plug it into the reduced function. Not all rational functions have holes, so that step gets skipped quite a bit. Next is your vertical asymptotes. So vertical asymptotes occur from the remaining factors in the denominator. So if one canceled, it creates a hole, but if it didn't cancel and it's in the denominator, then it's going to create a vertical asymptote. And since these are vertical lines, when you write their equations, you write x equals. You don't just write the number, you have to have that equation. Steps 4 and 5 are intercepts. These are just easy points to find. You don't have to find intercepts, but like I said, they're the easiest points to find. So x-intercepts occur when the actual function equals 0. So you set the function equal to 0 and solve for x. The really cool thing about rational functions and the x-intercept is that due to that zero product property that we have learned about, anything times 0 equals 0, the x-intercepts will always be the remaining factors in the numerator. And just so you know, it's possible for these rational functions not to have any x-intercepts. Y-intercepts, you know that's f of 0, so you just plug in 0 into the reduced function. Number 6 is probably the toughest of all of them, and that's the end behavior asymptote. And it says it's the horizontal asymptote, but it can also be a slant or oblique asymptote. And the way you find these is by comparing the degree or the highest power in the numerator to the degree in the denominator. So if you do that comparison, there's 3 choices naturally. Either the degree of the numerator, which we'll call p, is less than the degree of the denominator, which we'll call q. If that's the situation, then the horizontal asymptote is just y equals 0. So anytime p is less than q, y equals 0 is your horizontal asymptote. If the degree in the numerator equals the degree in the denominator, then you take it a step further and you take the ratio of their leading coefficients. So this says y equals a over b, and a is the leading coefficient in the numerator and b is the leading coefficient of the denominator. If p is greater than q, then there is no horizontal asymptote, but there is a potential for a slant or oblique asymptote if p is greater than q by exactly 1. So if 1 is degree 3 and the denominator is degree 2. If the numerator is degree 4 and the denominator is degree 3, that could produce the slant asymptote. The last step, step 7, is to find additional points on the graph so you can get a complete graph. Graphs like to coast along their asymptotes, so the graph is divided up by its vertical asymptotes, and then we just need to see if our graph likes to coast above its horizontal or below, above its slant or below, and so we're going to pick x values within the intervals that are divided up by that vertical asymptote and find a point, and if it's above the horizontal, then the whole piece of that graph will be above the horizontal. So we'll practice that when we're graphing. So example 1 is just to find the coordinates of the holes, if any exist. So remember, step 1 is to always factor, and step 2 is to realize that if a factor cancels, then that is the x value that's going to create the hole. So when I t-chart this up here, I'm going to get 2x plus 3 times x plus 2 all over x plus 3 times x plus 2, and what you'll notice is that these factors cancel, so that means that we have a hole at x equals -2. Okay, so that's the number, that's the x value that's going to correspond to that factor of x plus 2. So this does ask us for the coordinates, so we just need to take and plug in -2 into our reduced function. So we're not plugging it into the original, it's the simplified one. So we get 2 times -2 plus 3 all over -2 plus 3, again plugging it into here, and that's going to give me -1 over 1. So then my whole coordinates are at -2, -1. Okay, if you feel like you've got that, I suggest you pause the video and try B on your own. If not, you can just watch me do it right now. So again, step 1, especially when we're finding holes, since it deals with factors that cancel, we need to factor. So x plus 5 cancels, so the reduced fraction, the reduced function is 1 over x minus 5. So we know we have a hole at x equals -5. So we're going to take and plug in -5 into the reduced function. And you'll start to see with rational function graphs, the numbers are very rarely whole numbers or integers. They're usually rational numbers as well. Go figure, they're rational functions, but just be prepared for that. It's not always going to be this nice pretty number that you like to deal with. Sometimes you will have fractions, and actually more often times than not you will. So there's the coordinates of our hole there. So then we're going to move on to C, and we are going to factor. And you notice that no factors cancel there, so there aren't any holes in that function. None. And if you want to put your note, no canceling factors, just so you remind yourself why there was none in that one. But you can always go back over to step 2 on our list of steps to see that as well. Okay, example 2 is asking us to find the vertical asymptotes. So vertical asymptotes occur from the remaining factors in the denominator. So what we need to do is step 1 always is to factor. And since no factors canceled, the remaining factors in the denominator are going to become asymptotes. So we write them x equals -5, and you can do this just to put a comma between them, or you can write x equals -5 and x equals 5. So I just want to point this out real quick. In this function, it would have a hole at -2, -1, and the only vertical asymptote would be x equals -3, because that's the remaining factor in the denominator. Okay, let's look at this one right here. So first thing I'm going to do is try and t-chart the numerator, but it doesn't work out. But I can factor the denominator using a GCF. And so this right here, what value of x would make the denominator 0? It would be -1. So guess what? That's the remaining factor in the denominator that's going to make a vertical asymptote. Not too bad. Okay, now we're going to do the end behavior or horizontal asymptotes. So when you do these guys right here, what we need to do is follow these directions about P and Q. So step 1, I still want you to factor. And then the x minus 3's cancel, which means there would be a hole. Hopefully that's going up on your radar, and that our vertical asymptote would be x equals -2, but this isn't asking about vertical asymptotes. It's asking about horizontal. So what I've done is kind of like come up with this elementary school way of helping you out. So you need the highest power in the numerator. If it's a constant, that would be like x to the 0 power, so the degree is 0. And the highest power of x here is 1. So in this case, we have p is less than q. So if p is less than q, then our asymptote is y equals 0. All right, moving on to this one right here. I am going to factor it first. And notice that nothing cancels, so I can go straight to my P and Q analysis. So the highest power of x, if I were to unfactor it, is 2 in the numerator, and in the denominator it is 1. So P is greater than Q. So if P is greater than Q, then there is no horizontal asymptote. So we're going to write none. But you notice there's this little asterisk kind of style thing that says that if P is greater than Q by 1, then there can be a slant asymptote. We're going to practice slants on the back side, so we're just going to put slant. A slant is not a horizontal asymptote. A slant is a diagonal line. So it's a y equals mx plus b line. So we're not going to find it right here. We'll practice that on the back. Okay, for part C, we are going to factor. Now what I'm going to do first, just to make my life easier, is factor out the negative. I think it's so much easier for me to factor if I do that. So I factored out that negative right there. Let's see if any factors cancel in this problem. Ooh, look at that right there. Those factor right there. So this reduced form is negative x plus 2 over x plus 3. And if I simplify that, or sorry, this is not any more simplified, but if I multiply that negative out, this is the reduced expanded form of the equation. And so now I'm ready to do P and Q. P, highest power of x here is 1. Q, highest power of x is 1, which is equal. So what does this say? If it's equal, then you take the ratio of their coefficients. So y equals a over b. The leading coefficient here is negative 1, and the leading coefficient here is 1. So we get y equals negative 1. Okay, we're just about ready to put all this together to graph these things, but let's practice our slants on the back side. So to find the equation of slant of any of the function. So before we determine whether or not it has a slant, we are going to do P and Q. So P is 2, Q is 1, so this is greater. P is greater than Q by 1. So that's the only time you have a slant. If it was greater by 2, you wouldn't have a slant. So how do we find the equation of the slant asymptote? To find the slant asymptote, use long division to divide the numerator by the denominator. The equation of the slant asymptote will be the quotient. Disregard the remainder. Sweet. So when I do these problems, sometimes I don't even finish it off and find a remainder because I'm disregarding it anyway, so why do that? So I'm still going to check just to make sure that none of these cancel. And some of you can do this step in your head. You know it's not going to cancel because both of these factors have to be positive, so nothing would cancel with this one that has an x minus 1. But just to be on the diligency side, that's what we're going to do. So this is what it says. It take your denominator and see how many times it goes into your numerator. Which, by the way, is exactly what that's a division problem right there. So x squared divided by x equals x. So I'm going to multiply backwards, minus x squared minus negative x. These cancel, plus plus 4x plus 2. Okay, so again, this was minus x squared minus negative 1x. So that ended up being a double negative and making it positive. Then I have 4x divided by x, which is 4. So this is plus 4 minus 4x minus negative 4. And you can see we're at the point where we're going to have a remainder. We get to disregard once we get there. So you can do the math, you'll see that it's 6, but you don't have to. What we're interested in is that quotient. So our quotient is x plus 4. So that, my friends, would be the equation of the slant asymptote. Pretty cool. This one's just slightly more intense. It says find the equation of the slant asymptote. Again, we always are doing our factoring just to check. So x minus 6, x plus 1, all over 2 times x plus 2. So none of those can cancel. So if I do p and q over here for this one, p is 2, q is 1. So we're talking about the degree or the highest power there. And so p is greater than q and by 1. So that means it's going to be a slant. So we take 2x plus 4 and we divide it into x squared minus 5x minus 6. And this is kind of annoying, but what we're doing is x squared divided by 2x, which equals 1/2 x. Okay, so if I were to reduce that, I would get x over 2, and another way to write x over 2 is 1/2 x. That's just a fraction thing, so I'm not going to spend tons of time on it, but then you can always get a refresher if you need one in class. Don't forget to ask me. 1/2 x times 4, so half of 4 is 2, so that's minus 2x. These cancel. Negative 7x minus 6, so I'm doing negative 7x divided by 2x. So we did x squared divided by 2x, and now we're doing our next division, negative 7x divided by, so that's minus 7/2. And guess what? I'm just going to stop right there and disregard the rest because it's going to give me only the remainder, and I do not need that. I just need the quotient up top there. If you're not sure when to stop, then you should keep going. Don't try and take shortcuts if you're not ready for them. Alrighty, so let's go ahead and start graphing these. There's 7 steps on the front, so I'm going to put steps 1 through 6 on a chart. And then step 7 is to plot points, and I'm just going to do those right underneath the graph. So 1 is to factor, and guess what? It's so cool. This one doesn't factor. Okay. Step 2 of our steps is to find any holes. Since no factor cancels, this is none. So I'm just going to write no canceling factors to remind myself. Step 3 is to find your vertical asymptotes, which are the remaining factors in the denominator. So that's just going to be x equals 3, only one vertical. Step 4 is to find your x-intercepts. So that means you set f of x equal to 0 and the numerator, but this is a false statement. So guess what? There are none. So therefore none. Step 5 is your y-intercept. So to find the y-intercept, you plug in f of 0. So that gives me negative 1/3, and I'm going to write it in intercept form, 0, negative 1/3. Step 6 is that horizontal. So I'm going to do P and Q. So P, because the numerator is a constant, that's like x to the 0, so its highest power of x is 0. Here is 1. When I compare those, P is less than Q, therefore it's y equals 0. And again, that's on the front. So once you get through your chart, you're going to plot all those things that you have. So intercepts, holes, whatever you got. So I have x equals 3. So I'm going to go to 3. I'm trying to draw straight lines because you guys know I have OCD about stuff like that. So 1, 2, 3. Bam, 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 bam. y equals 0. I like the horizontal ones next. 1, 2, 3, 4, 5, 6, boop, boop. Okay, and then any points I have, I didn't get any from here. I don't have any holes. I don't have any x-intercepts. Oh, 0, negative 1/3, which is like here. Now, these graphs like to coast along their asymptotes. So if we go back here and read about these additional points, some functions require additional points to get a complete picture of their graphs. To find additional points, use the vertical asymptotes to divide the graphs into intervals, as graphs like to coast along their asymptotes. So the outside intervals require only one additional point to determine the behavior of the graph. So you just pick an x value from the intervals and plug it into the function to find the y value. The inner interval, if there is one, so sometimes in our situation that we have right now, we don't have an inner interval because we just have one vertical asymptote. You'll see the inner interval in the next problem when we have two. The inner interval requires 3 additional points to determine the behavior of the graph. Pick 3 x values from the middle interval and plug them into the function to find their corresponding y values. Okay, so let's flip back and apply that to our graph. So first of all, the graph is only going to be either above its asymptote or below its asymptote. Okay, so we have this vertical asymptote. It's dividing our graph into 2 pieces, and then we have this horizontal asymptote, which is also then dividing it into 4. So our graph is either going to coast along the top and side of this vertical asymptote, or it's going to come this way. Because I have a point down here, guess what? I already know that it likes to coast down here. So that's awesome, but I don't have a point to the right of this vertical asymptote, so I'm going to pick any x value in this interval. So you could pick any x value. I can pick 4, 5, 6. I obviously don't want to pick 3 because if I pick 3, the asymptote, it could be 3 minus 3. I can pick 3.1. I'm just going to pick f of 4 because I like those integer numbers and I think it's going to be easier. So 1 over 4 minus 3 equals 1 over 1, which is 1. So when I go to 4, x is 1. So does this graph like to coast above its horizontal or below? It likes to coast above. Okay, there's that graph. Okay, let's move on to the next one. This one right here says graph f of x equals 2x squared over x squared minus 4. So again, I'm going to start my 1, 2, 3, 4, 5, 6, 7. So the first step is to factor. So I get 2x squared all over x plus 2 times x minus 2. And since no factors cancel, in step 2, I'm going to write none. So there are no holes because there's no canceling factors. In step 3, I'm going to find my vertical asymptotes, so x equals negative 2 and 2, because those are the non-canceling factors remaining in the denominator. Step 4, I find my x-intercepts, so those are the non-canceling factors left in your numerator. So I'm setting the function equal to 0, just the numerator, and then I get solving this, I would get x squared equals 0, so x equals 0. So 0, 0 is 1. I'm going to show you how to find the y-intercept, but I already know the y-intercept is also 0, 0 because the x-intercept is 0, 0. So that's going through the origin, so that would mean it's both, but just for thoroughness' sake, that sounded right, I get 0 over negative 4, which is 0. So it would be 0, 0 also. Okay, and then step 6 is our P and Q. P, and this is where we would also do our slant asymptote if there is one. So let's see. So P equals 2, that's the highest power of x. Q equals 2, that's the highest power of x in the denominator, so they're equal. So therefore, we are going to do y equals a over b. So 2 over 1, the ratio of their leading coefficients. So y equals 2. That's a 1. Ignore. Let's make it like a really fancy one. You could hardly tell. Okay, so y equals 2. So once you get that far, you're going to plot on your graph. And step 7 is this stuff right here that we did. So I'm just going to plot mine rather quickly, as fast as I can go and still be neat. So we have -2 for one vertical, 2 for another vertical. These things are so cool when you think about it. I know they're kind of tedious, but they're also pretty awesome. Like their end behavior and things like that are determined, like if you think of limits and stuff like this one, as x's are getting larger, your asymptote is what the graph is doing. It's going to 0, and if you look over here, as the x's are getting negative, it's also getting to 0, so that's another way to tell your asymptote, your horizontal asymptote. But I digress. So any points I have, I only have 1 point. I have 0, 0 right there. So I need to know in this first outer interval here what my graph is doing. Is it hanging out above its horizontal or below? So I'm just going to pick an x value anywhere in this interval. So from not including -2, but -infinity up to just -2. So the easiest one is just to pick 1 over, in my opinion. So I'm picking f of -3, and I'm just plugging that into the function to find the y coordinate, which this would give me -3 squared times 2, so 18 over 5, which is 3 3/5. And since my horizontal is at 2, at -3, it's going to be 3 3/5. So this particular one wants to coast above in that first interval. Now, when I go to my middle interval, I have 1 point, but we recommend that you pick 3, one to the left and one to the right, just because this graph, instead of going, you don't know what it can do, but it has 2 choices. Let me pull out my little pad paper here. So this is kind of where we're at. A very rough sketch, and this graph is either in this middle interval going to do something like that, or this graph is going to do something like, it could do something like this. And that's super weird, but it's allowed to cross a horizontal. It's not allowed to cross a vertical. I guess it could also go this way too. So you can see why we pick 3 points, because if we pick 1 negative and 1 positive and the intercept, then that'll tell us the way that this graph is going. So I'm going to pick -1, and I'm just going to tell you when I plug in -1 to the function, I get -2/3. Okay? And then when I plug in +1 into the function, I also get -2/3. And again, I'm just plugging it in, but I'm trying to save us a little bit of time. So this graph is turning around. Instead of crossing through its horizontal, it's turning around. And then f of 3, and why am I picking 3? Because I need to figure out what the graph is doing here. So I'm picking 1 to the right, but I could really pick any number. I could pick like 1,000,000 and plug it in there, and if it's above the number 2, then I know that graph is coasting along above its asymptote. When I plug in 3, I get 3 3/5 again, just like I did on the other side, which makes sense because if you guys look at this, this function is an even function. If I plug in -x squared, then everything stays the same. And if it stays the same, then it has symmetry with respect to the y-axis. And look at this graph, totally will. So you can use symmetry as well to graph these, but it's just one extra step that I just didn't think was as beneficial as what we already are doing. So judgment call for me on that part. Okay, this one right here we have to graph. So again, some of you are already noticing what's going to happen here that hasn't happened in our graphs yet, I hope. So step 1, f of x equals x plus 3 all over x plus 3 times x minus 3. So when I cancel, bam, bam, this is 1 over x minus 3. So that's the reduced function. So then what I'm going to do next is find the wholes. And since x plus 3 was a canceling factor, there's going to be a whole at x equals negative 3. And to find the coordinates, I'm just going to plug negative 3 into the new reduced function. If I plug it into the old function, I'll just get undefined because I'll have division by 0. And I get negative 1/6. So my whole is at negative 3, negative 1/6. And I'm actually going to go plot that right now because I don't want to forget to do it. So that's where my whole is. Step 3, it's going to be our vertical asymptotes. So looking at the remaining factors in the denominator, x equals 3. Step 4, find your x-intercept, 0 equals 1. That's a false statement, so therefore there are no x-intercepts. But if I want you guys to notice, we're actually graphing a variation of this one. So it's going to look very similar to this one, but there's going to be a hole in it. Step 5 is to find our y-intercept. So we plug in f of 0. 1 over 0 minus 3, so that's negative 1/3, so our whole is at 0, negative 1/3. Not our whole, our y-intercept. Step 6 is P and Q. P, Q, P is 0, Q is 1. I'm going off of the reduced function, but even if I didn't, it's still less than. So I get y equals 0. Okay, and then before I do step 7, which is those additional points, I'm just going to draw everything that I have. So I have x equals 3, y equals 0. That x equals and that y equals is super important. Some students forget it, but keep in mind you're describing a line. And if I just say 3, 3 is a value. You need like an x equals or a y equals to say what kind of line it is. Okay, so believe it or not, even though this isn't a point and it's a whole, it's telling us that our graph is down in that quadrant because it was coasting along and then it had to take a break for just a split second, meaning a whole, and then continue going. So I don't even have to plug in a value in that interval because I already have what I need. Okay, let's pick one in this one. So f of 4, just plug it in. And since we already did it, we do know that this is this is just 1. So when x is 4, y is 1, so it's coasting up above, just like it did in example 5. Okay? Last problem is going to be the slant asymptote one, because we do need to practice that skill as well. So this is what you're going to do. Same steps, it's just step 6 that we're going to get to. That things are going to change. So step 1 is to factor. Plus or minus cubes, factors, little and big, parentheses, a squared, b squared. The signs go soap. And then down below we have our difference of squares. It's kind of nice when things don't cancel because then you don't have a hole, but it's also kind of not nice because if you have a hole, you know where the graph is going because it's coasting along those asymptotes and taking a little break. But this one is none because we had no canceling factors. Step 3 is going to be x equals negative 3 and 3 because those are our remaining factors in the denominator which determine vertical asymptotes. I just want to touch base on that real quick and just point out, like, as a more intuitive, like, thinking conceptual thing, this asymptote right here is saying don't equal me, don't touch me, right? And that's why our vertical asymptotes are where the denominator equals 0. Just, you know, making some connections. Okay, 4, this is a little interesting because we are going to have x-intercepts at the non-canceling factors in our numerator. So that means we have this right here. So we know there's going to be an x-intercept at 1, but then we have this right here. And we're like, okay, do quadratic formula to find it? Yes. Can I use the graphing calculator to find it? Yes. The other thing that I'm going to do, just to tie into what we've already talked about because I think it's easier, is I'm going to do the discriminant, which is underneath the radical of quadratic formula. b squared minus 4ac, so I have 1 squared minus 4 times 1, which equals 1 minus 4. It's negative 3. What that tells me is that the solutions to this equation right here, or the zeros, are imaginary. So am I going to see them on a real number graph here? No. So the only one I'm going to get is x equals 1. What a great problem. Okay, 5 is f of 0. That means it's your y-intercept. So you're going to plug in 0. And you're more than welcome to plug it in here, but you also kind of like need to be efficient. So I'm going to plug it in here. It's the same exact equation, but way less x's. So then I get 1/9. So 0, 1/9. I really want you guys writing out the coordinates of x and y intercepts. Step 6. Okay, here's where things take a turn. P and Q. P is 3, Q is 2, P is greater than Q, so there is no horizontal. But, big but, I said big but, sorry, childish. There is a, because P is greater than Q by 1, a slant exists, or oblique. I like slant. So how do we find the equation of the slant? We're going to take that long division that we've already practiced, and because I don't have all the powers of x, I'm going to write them in there with zeros in front. So x cubed over x squared is x, and then minus x cubed, and then minus negative 9x. Those cancel, plus plus 9x minus 1. This is actually going to be disregarded because this is my remainder. How do I know when I'm at my remainder? I know I'm at my remainder when the power here is greater than the power here, right? Does that make sense? Like I can do x cubed divided by x squared, but I can't do 9x divided by x squared. Okay, so then the equation of my slant is y equals x. So let's go ahead and graph all these. So we have the negative 3 and 3. Don't mind my dog. I think he's having a little doggy nightmare. Or he's like chasing something. We'll see. If he keeps going, I might stop him. Okay, y equals x is the next one, so that means the y-intercept is 0, 0, and then you go up 1 over 1. Watch out for these graphs. For some reason, they are not squared off. So I'm drawing dots everywhere just because I'm liking to be pretty exact, but you guys get it. Okay, so, whoa, what's happening now is a couple of things. So first of all, here's that vertical asymptote. It's either going to be above the slant or below the slant. So one thing I'm going to do though is plug in some things I do know. I know that I have a y-intercept at 1, 0. So I'm going to plot that. So that's here. And I know I have one at 0, 1/9, which is right here. It's kind of crossing its slant, so I'm predicting that it's going to do kind of the cubic shape rather than the parabola shape, but we'll see. So I'm going to pick a number in this interval. So I'm going to pick f of negative 4 and plug it in. So negative 4 cubed minus 1 all over negative 4 squared minus 9. So that gives me negative 63 minus 1 all over 16 minus 9, which gives me negative 64 over 7, which gives me negative 9 and 1/7. Oh, wow, I just did all that without you being able to see it, but you get the idea. It's fine. I'll leave it here in chat for a second. So negative 9 and 1/7. So when I go to negative 4, is it going to like to be up and coasting along here? Or is it going to be like to be in that little triangle area, which just looks like a triangle, but remember these asymptotes keep going, so it isn't just a triangle. So -9 and 1/7 is about here. So since it's below its slant, it likes to do that little thing, coast there. Then I'm going to pick f of -1, and when I do that and plug it into the equation, I get 1/4. So it was at 1/9 and it's going up. So that's my clue that it's gonna do that kind of thing right there. Okay, so if these 2 points were at the same height, it would be a parabola. It would mean that it's a turning point because it would be increasing and then you would see it decreasing again. So, but since that's not happening, right, it's decreasing, 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 and decreasing, it's going to take on that shape. All right, last interval over here that I'm trying to get, I'm going to do f of 4. And when I do f of 4 here, I actually just get a nice clean old 9. So 4 and then 9 is right here. And then it's going to be like that. So that's what our cool looking graph looks like. So yeah, that's it. Have a great day.